but I'm going to talk today about engineering intrinsic electron correlations in van der Waals materials. By intrinsic here, I mean without the need for any heterostructures from moires. And the appeal of this is that we can combine sort of conventional bulk characterization for correlated materials with potential 2D measurements. Okay, so I'm going to discuss two different projects today. First, some published work on two-dimensional heavy fermions in this material, cerium silicon iodide, and then some unpublished work on a 1D charge density wave in a 2D magnetic material. So to start off, in this first project, let me introduce the Kondo effect for those who are maybe unfamiliar. The Kondo effect stems from the interaction between carrier electrons and localized magnetic moments in a material. At the relatively dilute limit of paramagnetic spins at high temperature, this is really just resulting in a simple spin-flip scattering process. But as we cool this sample, the carriers start to screen the local magnetic moment, and this creates what we call a Kondo singlet. But if we have an array of these paramagnetic spins, instead of just having a single Kondo singlet, we actually form this coherent Kondo lattice, which gives rise to correlated transport derived from these heavy electron states that are hybridized between the local spin and the carrier electrons. In practical measurements, we can see here some resistivity data where we introduce increasing amounts of cerium into copper. At the very low concentration limit, we have an increase in resistivity as we go to lower temperatures caused from this spin-flip scattering that eventually saturates as we start to form Kondo singlets. Whereas in the case of a dense array of cerium, instead of just saturating, we form this maximum, and then the resistivity begins to decrease, and this is tied to the onset of the Kondo lattice. From more of a band structure picture, this is reflected by the presence of these flat bands right at the Fermi energy coming from the 4f electrons, which are extremely localized, which gives rise to this very large effective electron mass. And when these hybridize with light electrons coming from other elements, we form this hybridization gap, ideally right at the Fermi energy. And the real appeal of studying the Kondo effect is summarized by this phase diagram called the Doniak phase diagram. As it turns out, this interaction between carrier electrons and localized magnetic moments doesn't just tie to the Kondo effect, but also to the RKKY interaction, which favors magnetically ordered ground states. And the competition between these two is what gives rise to interesting properties. So at relatively weak couplings, the RKKY interaction dominates, which gives rise to these magnetic ground states. But as these two exchange terms become comparable, we start to see a suppression of magnetic order, giving rise to this quantum critical point. And then at the strong coupling limit, we have this expectation of a heavy Fermi liquid ground state. And so this is really the regime at the quantum critical point that we want to access, where we suppress magnetic order and can give rise to more interesting phenomena, especially superconductivity. So conventionally, the way we would sort of tune along this x-axis is using things like doping or pressure or magnetic field, all of which can be used to destabilize the magnetism in favor of a stronger Kondo effect. But a more recently established tuning parameter is the idea of dimensionality. So if we think about this three-dimensional cubic structure, cerium indium-3, it's a Kondo antiferromagnet with a magnetic ordering temperature of about 10 Kelvin. If we introduce this non-magnetic spacer layer, so for instance in this compound, cerium cobalt indium-5, we instead have these sort of quasi-2D tetragonal layers of cerium, and this suppresses the magnetism pretty dramatically so that this material is a quantum critical superconductor with a critical temperature of about 2.3 Kelvin. Alternatively, people have shown that if you take MBE-grown superlattices, where you have a single layer of cerium triindium separated by several layers of the non-magnetic lanthanum triindium, you can again suppress the magnetism and access a quantum critical regime. But both of these approaches have some issues. In this case, not only do we have to identify whole new compounds to achieve this, but we also don't fully suppress the three-dimensional interaction. And in this superlattice approach, we have a lot of issues where the size mismatch between lanthanum and cerium gives rise to strain that can suppress the superconductivity. And so what we really want for studying these materials at two-dimensional limit is a van der Waals material where now we can access the enhanced Coulomb interactions and magnetic fluctuations that can promote quantum criticality in these materials. And on top of that, we can take advantage of all the tools that have been developed for van der Waals materials over the past 20 years. But this presents a bit of a challenge. Heavy fermion physics has generally been restricted to these three-dimensional intermetallic materials. And so if we want to put this into a van der Waals compound, we sort of need to take a slightly different approach. And so our route to doing this was looking for an intermetallic structure that we could dimensionally reduce to find a van der Waals compound. And so we start from this aluminum diboride structure, which has these triangular layers of a rare earth ion. In particular, we want cerium, separated by these honeycomb layers of p or d block elements. In this case, as we start to introduce halides into this structure, we can first access this sort of intermetallic structure where we have 2D intermetallic slabs that are bound together by halides. And then if we introduce even more iodide, we can now realize this van der Waals structure where these intermetallic slabs are fully disconnected from each other. So this is the material I'll discuss today. Its formula is cerium silicon iodide. In this case, the honeycomb layer is composed of silicon. It's basically a silicene layer sandwiched by cerium ions and then iodide capped. Because this is a van der Waals material, we can readily exfoliate this. So here I'm showing a relatively large tri-layer flake that we can access, but we can routinely find even thinner down to the monolayers. So as I mentioned, a big aspect of this is that we can use traditional bulk characterization. So here I'm showing heat capacity data, and from this we can extract the Sommerfeld coefficient, which correlates with the effective electron mass. What we find is that for the cerium version of this material, compared to the lanthanum, which is non-magnetic, the Sommerfeld coefficient is 40 times larger for cerium, which is a signature of enhanced effective electron mass and large electron correlations. Similarly, in transport, we see some signatures of non-conventional behavior. At high temperatures, our resistivity is relatively flat. Below about 50 Kelvin, we start to see this sort of broad drop. And then at lower temperatures, we see a sharper drop coming from magnetic ordering. But the most interesting feature here is this sort of anomalous change in the resistivity below about 50 Kelvin. And we can really start to understand this using spectroscopic tools. So here, I'm showing ARPES data for the cerium compound on the left and the lanthanum on the right. We can see that for the most part, their band structures are quite similar to each other in terms of their dispersive bands. And the main difference is these two flat bands, one right at the Fermi energy and one slightly below in the cerium case. These are two different 4f states where they are split by the spin-orbit coupling of cerium. And so the fact that we see these bands right at the Fermi energy is a first confirmation that we do in fact have a Kondo interaction in this material. To study this more closely, we can look at this sort of crossing between a light band and a flat band. And if we zoom in, we can see that we actually do have a forbidden crossing with the formation of a hybridization gap. We can study this as a function of temperature. And basically what we find is that we see this gap that slowly closes as we warm and is basically fully gone right around 60 or 70 Kelvin, which quite closely matches the feature we see in transport. I'll note here that the reason that we're studying this sort of lower energy band is just because it's easier to see. But the actual relevant hybridization would be right at the Fermi energy. This is simply difficult to see in ARPES measurements. But we can study this more carefully using scanning tunneling spectroscopy. So here I'm again showing the local density of states from STS measurements on the cerium version and the lanthanum version. And we see that only in the cerium case do we see this sort of dip hump feature that corresponds to a Kondo resonance. If we take the line width of this as a function of temperature, we can again extract a Kondo temperature of about 74 Kelvin. And so the really close matching between the feature we see in transport, the closing of the hybridization gap in ARPES, and our Kondo temperature extracted from STS measurements all support that the main features that we're seeing are tied to the Kondo interaction in cerium silicon iodide. Given that this is a van der Waals material, we can study the extent to which its electronic structure is actually two-dimensional, which will be very important if we want to study this at the 2D limit. Here we can probe this using quantum oscillations. So these are Shumnikov de Haas oscillations, where we measure as a function of angle relative to the c-axis. We can see that as we start to tilt away, these oscillations remain in phase with each other, which is characteristic of a cylindrical or quasi-2D Fermi surface. And as we tilt too far away, these oscillations are fully suppressed. Similarly, we can directly visualize this cylindrical Fermi surface in ARPES, where we see that the Fermi surface is basically independent of the Kz value. And so all of this tells us that even in bulk crystals, the electronic structure of cerium silicon iodide is already quite strongly two-dimensional. And this allows us to perform 2D transport measurements. And this was in collaboration with Philip Kim's group at Harvard. So here I'm once again showing the bulk transport data on cerium silicon iodide. If we compare this to resistivity measurements on a 15-layer flake, we see the exact same feature around 50 Kelvin and at 7 Kelvin. And if we go even thinner to 4 layers, we again see a broad drop around 50 Kelvin and a magnetic ordering transition at 7 Kelvin. And we have since done this even thinner on bilayer samples. And so what we can really see, quite remarkably, is that the Kondo physics and magnetic order are almost entirely unaffected by confining these samples to 2D. And so on one hand, this is a great success. This means we've succeeded in our main goal of confining the Kondo effect to a single van der Waals layer, where we can now use some of these van der Waals techniques to study this sample. But in a sort of broader sense, this isn't exactly what we had hoped. Our hope was that as we lowered the dimensionality, we would be able to shift across this phase diagram. But as it turns out, because this compound is van der Waals, it's so strongly two-dimensional that dimensionality no longer becomes a good tuning parameter. And so for the sake of time, I'm going to stop there on this project. But I'll very briefly highlight that we can do a lot of chemical modifications of this material to access a range of different properties. And I'm happy to discuss that after if anyone's interested. So for the second half of my talk, I want to talk about some newer results on this sort of quasi-1D charge density wave in a 2D magnetic material. The material I'll specifically be discussing is chromium sulfur bromide, and I think you'll hear quite a few talks on this material this week. So this material is a van der Waals magnet with an orthorhombic crystal structure. So this means its two in-plane axes are crystallographically distinct. As a magnet, the pristine material is an A-type antiferromagnet, where the spins align along the B-axis within each van der Waals layer, but antiferromagnetically between adjacent layers. As a semiconductor, its most interesting property, or to me, is this extreme anisotropy of the conduction band. We can see that along the gamma X direction, which corresponds to the A-axis, the conduction band is quite flat, whereas along the gamma Y direction, which corresponds to the B-axis, it's quite dispersive. And this leads to some really strongly anisotropic semiconducting properties. But what I'm going to be discussing today is what might happen if we can shift the Fermi energy up into this conduction band by electron doping. You might imagine that the 1D character of this can give rise to a variety of different electronic phases, and we can start to understand how those couple to the magnetic order. So we achieve this by using lithium intercalation. So by reacting the pristine material with this strong reductant, we can intercalate lithium ions in addition to these THF molecules, which are neutral, but are just the solvent of the reaction. We can intercalate about 0.18 lithiums per chromium. Each lithium transfers 1 electron to the van der Waals layers. And so in a 2D sense, this corresponds to an electron doping of about 2 × 10⁻⁴ per centimeter squared for each van der Waals layer. OK, so the first thing we need to do is confirm that we haven't destroyed the material. So by powder X-ray diffraction, we can see that we still have a van der Waals structure. The interlayer spacing increases from about 8 angstroms to about 12.5. And this is particularly large because of the co-intercalation of these solvent molecules. We can use pair distribution function analysis, which basically tells us that the in-plane bonding remains intact. And we can additionally perform electron diffraction to show that the orthorhombic lattice is still present. But if we look more closely at the electron diffraction, we can see that in addition to these lattice reflections that I'm highlighting here, we also see these sort of weak satellite reflections, which suggest some sort of structural superlattice. And we can visualize this in real space using scanning tunneling microscopy, where here we can see a modulation running along the B-axis that gives rise to these apparent stripes that run along the A-axis. And just like in the electron diffraction, by either counting the atoms or looking at the Fourier transform, we can see that this is about 7 times the periodicity of the lattice. If we take line cuts along the 2 crystal axes, we can see that along the b-axis, we get this very large modulation coming from what I'll show is a charge density wave, whereas along the a-axis, we only see oscillations corresponding to the lattice. And this really highlights that this is an extremely one-dimensional feature running exclusively along the b-axis. OK, and so to really confirm that this is a charge density wave, we can use scanning tunneling spectroscopy. So here I'm showing the STS of the pristine material, which just shows typical semiconducting behavior. When we electron dope using lithium intercalation, we start to see the presence of states around the Fermi energy. And more importantly, we start to see this partial gap that opens right around the Fermi energy. If we take STS at the sort of bright spots, which are peaks in the topography or valley in the topography, we can see that the local density of states is modulated. So this tells us that this isn't just a structural change, that we actually have electronic differences between our two sites. And if we actually look at the magnitude of the gap, we can see that it's several hundred millielectron volts, which is quite high temperature, or which should correspond to an onset temperature well above the 40 Kelvin that we're measuring here. And so in fact, if we do similar STM measurements at room temperature, we can see a modulation with the exact same periodicity. In this case, we can't achieve atomic resolution, so we can't do all the STS measurements that I just showed. But the fact that the modulation is exactly the same as at low temperature suggests that this charge density wave persists well above room temperature. To better understand the anisotropy in this, we can perform optical reflectivity measurements in the infrared. So here I'm showing for light polarized along the A or B axis. So when we measure along A, which is the direction of the stripe, so orthogonal to the modulation, we can see this Fabry-Perot interference, and this is just because we're measuring on relatively thin flakes. So this tells us that the material remains a semiconductor along the A-axis. But along the B-axis, we see this sharp plasma edge, and then instead of just approaching unity, we see this dip as we go to lower energy. We can study this dip as a function of temperature, where we see it broadens, which is exactly what we expect for a charge density wave gap. And more importantly, if we fit this data, we can see that this gap is right in line with what we observe in STS measurements. And similarly, the carrier densities that we extract from these fits pretty nicely align with the values we expect based on the extent of lithium intercalation. Doing resistivity measurements along the direction of the modulation has proven quite hard, but we can do this along the A-axis. Just like in the reflectivity, we see that the material remains a semiconductor, though I'll note that the resistance is much, much lower than for the pristine material. And right around 200 Kelvin, we see this sort of change in the resistance, which corresponds to the magnetic ordering temperature of the intercalated compound, and I'll come back to that in a second. So far, everything I've said suggests that the 1D character of this conduction band is what's giving rise to this charge density wave. And so from that, we might think that this is largely Peierls mediated and not really tied to electron interactions. But in fact, if we think about what STM is actually looking at, in this material, the two chromiums are not equidistant from the surface. We have sort of chains that are closer to the surface and then chains that are further away. And so in an STM tunneling measurement, we only expect to see the chromiums that are closest to the surface. So we can ask what is happening to these lower chromiums. To study this, we did tight binding calculations where we can replicate this sort of charge density wave state. And what we find is that between adjacent chains, there's a pi phase shift in the charge density wave. So the peak in charge density for one chain is next to the minimum in charge density for an adjacent chain. And so in STM, we only see sort of the dark blue circles here, which gives rise to this in-phase behavior. And so what's quite striking is that we can see that this pi phase shift is mediated by a Coulomb interaction between adjacent chains. So really what we can think about is that we have sort of 1D chains running along the b-axis, but that are weakly tethered together by a Coulomb repulsion. And while we can't directly probe whether this Coulomb repulsion is real, one thing we can say is that the theory predicts a very large charge modulation where the difference between the maximum and the minimum in charge density is about 0.26 electrons per chromium, which is much larger than for a conventional charge density wave. And if we take STS spectra along the direction of the modulation, we can actually see that the valence band maximum is modulated by the charge density wave. And that's really consistent with our theoretical predictions that suggest this extremely large charge modulation. So coming back now, very briefly, to the magnetism. As I mentioned before, chromium sulfur bromide is an antiferromagnet with an ordering temperature of 132 Kelvin. After intercalation, we see two main differences. The ordering temperature is greatly enhanced to about 200 Kelvin. This is mostly tied to the effects of electron doping. We also see a change in the interlayer coupling from antiferromagnetic to ferromagnetic, and this is primarily tied to the increase in the interlayer spacing, but electron doping is also predicted to change the sign of this interaction. And we think this makes this charge density wave quite unique. There are other examples of ferromagnetic charge density wave compounds, but typically you can envision there's some non-magnetic charge density wave band near the Fermi energy, and there may be local moments in the sample. When these local moments ferromagnetically order, you can get a spin splitting right at the charge density wave, and so you get a weak spin polarization, and effectively this has been called a spin density wave. For the intercalated chromium sulfur bromide, we think we have a slightly more strongly coupled system. So in this case, if we look at the band structure for just a monolayer of chromium sulfur bromide, we see that the conduction band is predicted to be spin polarized. And this is because all of these, both the valence band and conduction band, are derived from the d orbitals of chromiums. So we have a strong Hund's exchange between the sort of carriers in the conduction band and the local moments of the valence band. And so when we have this charge density wave, we actually have a spin modulation that's exactly equal to the charge modulation. And this is something that hasn't been observed. And we think that this should allow us to be able to manipulate the magnetism to tune the charge density wave, or potentially vice versa. So we think this is a really exceptional platform to study 1D physics and their interactions with magnetism. We already have some evidence that by tuning the extent of lithium intercalation, we can tune the CDW periodicity. We know that if we change the halide in this material, we can affect the interactions between the chains. And all of this that I discussed so far was on bulk crystals, but presumably we can also study this at the 2D limit using electrolyte gating, where then we can see if we can tune the charge density wave sort of continuously by changing the level of electron doping. So there's many, many people who contributed to this work. I won't thank everyone, but I'll just list them here, and I'm happy to take any questions.